Hello, can you hear me? Yes? Yes, okay, good. Thank you for responding. And today, we are going to do something interesting. You will like it, okay? So I'm sharing my screen, did I? I haven't. I haven't shared my screen. So we are going to have about 40 minutes today. Let me put a video panel, put my chat box. So I monitor the chat box. Okay. And I can hide this float. So welcome to today's second day of, wow, this is so big. Let me see. Of April. So this is our week 11b, okay? In the quiz, you are going to see that we have some questions you need to ask. So basically in the next 40 minutes, we are going to cover 3 topics. We'll see whether it's possible, okay? After that, we are going to have a half-hour orientation about final project requirements, going to be led by Furkan and also Hiro, our 2 capable TAs. I guess you also learn a lot from them. So we're going to do 3 topics, okay? The first topic is regarding internal model principle, IMP, internal model principle. Internal model principle. Okay, the second topic we're going to do today is regarding internal model principle regarding Youla parameterization. Okay, and these are going to be okay. The third one is called Smith's predictor. Okay. So we see whether we can do it. Obviously, we cannot do it, given time. Okay. So I'm going to give you the essence of the ideas. Okay, of the ideas. Then you go to. We have a PowerPoint on this one. We also have PowerPoint on this one. We also have PowerPoint with this one in our folder. After you learn about this basic ideas, it's not hard for you to follow those slides and fill in other details, okay? So I'm going to first start with internal model principle, okay? First of all, we have a signal, okay? We should say that if we have a signal, like say D of t, okay, D of t, we should understand that the D of t is always, any signal is always there's a generator, okay, generated signal, okay, generated signal. So what is that generator? So you can imagine that if you put the impulse response, impulse in here, then this is nothing but a DFS, right? DFS. So for example, if your signal is a step, so your generator here is 1 of S. So integration of impulse will get you a step, right? So make sense? Okay. So then I know that the D of S could be written as numerator D of S and denominator D of S, right? Okay. So say for example, in our case, we have a step that is 1 divided by S. But if you have sinusoid, so you have sinusoid T, okay? So then what you have is 1 over, this is S squared plus 1. So this is your, so in this case, D is S. In this case, D is S squared plus 1, okay? So these are the 2 examples to show you. So what internal model principle said is you have a system you have a plant. You want to control it. You design the controller. So this is CFS. Okay. So you have a reference signal. Okay. So in this loop transfer function we usually write is LS is a CFS and PFS. So then we can write this is like a numerator C, numerator denominator C, numerator C P, and denominator P. So numerator and denominator polynomials, of course, is a polynomial of S. Okay, I'm dropping the bracket S. Okay, so this also can be written as like numerator L, denominator L. Is polynomial. Okay, so this is a loop transfer function. Okay, internal model principle said that, so if this is a reference signal, or you have a disturbance signal in here, okay, disturbance signal in here, and you want this E steady state to be 0, okay, if you want this one steady state to be 0, okay, so this is a desirable steady state error is 0, okay. It's also called ESS, okay, steady state. When T is very big, your error is 0. So basically your output will track onto this one. But remember, I have two signals. One is R, so I have a numerator R, denominator R, okay. I also have a D. For the R is like this, for D is like this, okay. And D, usually I can say, oh, D is 0, so only consider reference. Okay, but it doesn't matter. We just write it in general. You can write ND divided by DD, okay, DD. So you can see DR, you have a DD, okay, DD. So this DR and DD is one is a reference, one is a, so one is a, disturbance. So this is called generators, denominator of the generators, okay? Generator characteristic polynomial, okay? So you have characteristic, you multiply them together, dr times dd. So if you have 1 of s, here you also have 1 of s, so then you have a square of s. No, that's not the case. We only count 1, okay? We only count 1. In other words, if you have step in here, then internal model principle said that in your DL of S, okay? DL of S is DL of S, should be able to participate, partition, okay? So it should contain this denominator should contain the dr, okay? And you have a dl. What is left is this one, okay? So you can split the dr out, okay? Split the dr out. So this sounds like strange, but it's not. Say for example, I have a step in here, okay? I want a 0 steady state error. What I said is the whole system has to be type 1, right? Type 1 means you have to have a S times DL bar. You can pull out an S. You can pull out S in here. Inside here, you have an S. You contain an S. You have an integrator in the loop. Either you have a integrator in here, or you already self-contained integrator in here, okay? So let me give you an example. Say for example, so you have a system that is type 0 in here. So you put a KP in here. So then this is a step. So you have 1 of S. In this case, your dr is s. But if you check this one, what is the dr? What is the dl? So dl is all the denominator adding together. It will give you ts plus 1. There's no s you can pull out. It's not possible, okay? So in this case, the zero steady state arrow in here is always not 0, okay? You cannot be 0. So then at least you need to consider the ki divided by s. So then you are going to have s. So in this case, your denominator dl will be st s plus 1. And this one can be written as a dr, which is s times ts plus 1. So you contain this dr in here, okay? So this is, you may say, oh, I know this. But remember, your reference could be anything. Say, for example, you have s squared plus 1, you have sinusoid in here, okay? So now, even if you have s in here, even if you have an integrator in here, so you have pi control of velocity loop, then whether the ESS will be 0, the answer is no, no way, okay? Okay, so how to make it 0 then? As I said, your controller has to have something what I called, okay, contain the dr. In this case, the dr is s squared plus 1. So in other words, you cannot change your plant. You can change your controller. So your controller has to be s squared plus 1 put in here. And here you put a k1 plus k2s. Okay, you can do that. You put this one in here. Then you have sinusoid in here. So then in this case, here you can make the ESS to 0. Okay. So that's called controller architecture issue. Architecture issue. So, but you say, oh, I also need, I have a 1 plus sine t in here. I have also a step constant. So what you should do? You should do another s in here. You need another s. Because in this case, dr is s squared plus 1. And this must be contained in the dl, okay, dl. So in this case, the dl is s squared plus 1 times s times ts plus 1, right? Okay, so that tells you, if you know what is your reference, the same thing applies to disturbance. If you say, oh, I have sinusoid disturbance in here, how to remove it? You need s squared plus 1 here, okay? Makes sense? So IMP basically says your loop transfer function denominator of loop transfer function denominator must contain the DRS, the characteristic polynomial of your generating signal. This is called generating signal, generating transfer function, okay? Times another part, whatever bar left, okay? So only when you contain this factor, okay? This is factor. So this factor is actually called internal model of your reference or disturbance, okay? Or other signals you inject in there, you want to reject it, you have to do that, okay? Is this too fast? So then basically I want to say that internal model principle is a generalization of system type concept. So because we only consider the system type as a 1 t squared, okay? We only consider this. So then you have a 1 integrator, 2 integrators, and 3 integrators in the loop, okay, to make it zero steady state. If you don't have enough, then you are going to have non-zero steady state for sure, okay? So this is called internal model principle in 16 minutes. Okay. Let me return back to this. Questions? I'm going to get to the next question, Youla parameterization, okay? So again, in summary, when you want zero steady state error, then you should say your controller plus multiply the plant, C and P, okay? C and P, the denominator combined should contain the internal model of your reference. That's why you need a S in here, type 1 for this case, okay? Overall type 1 to make a zero steady state error. So in the future, you have any type of R, okay? If you are giving an R of T of any form, you can do Laplace transform and get its denominator and contain that denominator into the controller, okay? It's called internal model principle, all right? Again, internal model principle is a generalization of system type concept. If you feel like system type concept is still not familiar with you, you should go and review what we learned before, okay? All right, so. We are going to learn next is called Youla parameterization. So there are several names. Sometimes people say called affine parameterization, or sometimes people say, oh, what is a control parameterization? So either way, okay. Does it come into play with, yes. If the D is have the same role as R, reference. So I only use reference as an example. I didn't do a D, but they should have the same meaning, okay? But you should not double count, okay? You should, it's like a intersection or union. So if you have a step, R is also, D is also a step, so you only do one, okay? One species, not double count, okay? Okay, so Youla parameterization. Let me ask you a very interesting question. So suppose P is open loop stable, okay? Meaning if you have a bounded input, you have a bounded input, you have a bounded output, meaning the system will not caught on fire or get exploded. It's already stable. But if you put a controller in here and start to say, let's close loop it, there are two results. That is, from here you have input, from here you have output. So the closed loop system might be stable or might be unstable. So you could, if you don't do the C properly, you could mess up this closed loop system to turn the stable system an unstable closed loop system. Make sense? So you have to choose C properly. So there are so many choices of C to still make this a CP divided by 1 plus CP. A closed loop system is use a T, is a complementary sensitivity function. Complementary sensitivity function, transfer function, okay, or closed loop transfer function, okay? You have two names, okay? Because there's a sensitivity function is called 1 plus 1 plus CP, and T plus S is 1, so that's why we'll use this complementary sensitivity function. This is called sensitivity transfer function, okay? Okay, so question is, if the C is not choosing properly, I could make the whole system unstable. But I want to find out all C's, okay, that stabilize a system, okay, closed loop system. So can you find all those stabilizing controllers to make the whole system stable? So of course there are infinite number of them. So, but however, infinite number of say for example, I have 1, 2, 3. So this is natural number. So it's not, it's infinitely and many. Okay, infinitely many. So infinitely number of integers here. But if you can map some infinite set to this set, then we call this is actually countable. So countable. So this is called countable. Although you have a family of things, there are infinite number of those. But if you can map this set into a natural set, then it's called countable. So I want something similar. Okay. Say for example, I have a family of all. This is all stable filters. Okay. All stable filter. This is a family. So if I can express C as in terms of all stable filters, then we call this is parameterized. Okay, parameterized. So that's the basic idea. So let me derive this one for you. Okay, so the beginning point is you consider this T is you have C1 plus Cp times P. So this is your closed loop transfer function, okay? So I know this is stable, okay? I know this is stable, but if I assume this is a Q, and Q is always stable from this family, okay? Q is from this all stable filters in here. We'll assume this is a Q. So what I can do is simply write this way. So C1 plus Cp is Q, okay? Is Q. So if I express the C in terms of P and Q, so then what do I have? So C equals Q plus Q, P, C, right? So move this guy this side, I'm going to get C equals Q divided by 1 minus QP, right? 1 minus QP. So in other words, if I choose C in this way, actually in this way, I put it back to this, then this red box will become a Q. Then this T will be QP. So P is stable, Q is stable, so T is stable. Then this is called C is in the parameter of Q. Okay. If you give me a stable Q, I can find a C. Put this C to this controller here, I'll get closed loop is like this. So isn't this beautiful? Yes. Okay. So this is actually called Youla parameterization. It's the person called Youla who discovered this one first. Parameterization. Okay. Okay. Very nice. But I want to do something interesting for you. So here, so you have a Q. Okay. So if I draw a block diagram here, okay, so you can see what I should do. So C is actually getting into remember, I put a plus in here because this has to be plus so that this is minus, okay? This is a minus. If this is a negative, then this is positive, remember? So it has to be a positive, okay? So basically, this is my signal E. This is my signal U. Then I put into the P. And then I put into my here. So this is my E. So basically, I'm having something here is called C. The C. This is my C. Well, the C has an equation like that. Q is a forward transfer function Q. and you have a loop transfer function QP, and you have a positive feedback. So then it's a negative in here. So if I do this one, y divided by r is what? Is t, my transfer function closed loop. I already did that. Q is Q times P. Is that right? Q times P. So, so this is easy. The reason we write this one here is, so in the future, I design a C. I have so many choices, big family of this one. I have an infinitely many. So how I can pick up one so that it is stable and optimal. So I need to search the C. If I search C, and remember, originally T is function of C, is C over 1 plus Cp times P. So this is nonlinear, okay? Nonlinear. But if I say I search Q, so I write T as a Q, so this is linear. Linear in Q. This is nonlinear in C. So this is actually much easier to search the best C. Much easier when you are linear, okay? So linear has another term, it's called affine, okay? Affine. So that's why they call affine, parameterization. Get it? The magic will happen next. I have two magics. So this first magic is, if I draw this one, you are going to see. So I'm going to redraw this whole picture. But I'm drawing in a way that is easier to understand. So you have P in here, you have output in here, Y. So here, so this one I'm going to do here. This is the point. I'm going to have a U in here. So this is my E in here, okay? So what I'm going to do is I pull out something here and do a P in here. And I do negative sign in here, okay? And do positive sign in here. So the difference, oh no, sorry. Be careful, okay? Look carefully here. So the difference here is 0, in fact, right? So then I have feedback in here, okay? So the plus or minus. So basically this thing, so you can see that this signal goes to P and plus to this one and reach Q. It's the same. It goes to P and negative, and I come over here negative again. So then it's the same as this one, right? Same as this one, reach to the Q. So these are equivalent, okay? And with equivalent here, because this is 0, so I can safely say, it's like broken. Here is broken. So therefore, from R to Y, Y divided by R, it is Q times P. Oh, this is exactly T as we said before. So one of the controller design is you try to make a copy of the system or as an estimation of it. Then you do this. So this is exactly a controller parameterization. And later on, okay, you say, oh, actually, this is my controller. This is my C. It's just like this box is just like this box, okay? It's the same. It's the same. So this is called Youla parameterization. The reason is this one make it linear, okay? It's linear. So it's easier, okay? To do optimal control design, because here you have infinite many such kind of Cs. If you choose one, you need to search, okay? According to criteria, to search the C. Then linear, when it's linear, it's easy to search. When it is nonlinear in C, so this is nonlinear in C, linear in Q, so much easier. So this is called Youla parameterization. So both equations like this, okay, and block diagrams like this, please. I guarantee you I'll check you in either in final exam or in some other places, okay? If you miss today's lecture and you don't watch the replay, you will be in trouble, okay? So let me review what we did here. So we did internal model principle is a generalization of system types. Then we talked about Youla parameterization idea. So we can find out all stabilizing controllers, okay, C. So if I give any of the Q, I can get a C. So I find all of the C's that stabilize the system. So this is called Youla parameterization. And you may say, wow, how come this is useful, you know? Now I'm going to show you number 3, called Smith's predictor. So I showed you this is some sort of magic, magic 1. I'm going to show you magic 2. Okay. So everybody knows that you have a system you want to control, but actually you also have a delay in here, okay? Delay in here. And you also have a controller you design in here, okay? So your closed loop transfer function is like this. C P E L S 1 plus C P E minus L S. So this is my T, okay? My T. Make sense? Okay. But this guy is very troublesome, okay? Very troublesome. And make this is no longer a polynomial. It contains something like that. You do a characteristic root analysis. There are infinitely many roots. It's so hard to do the checking, okay? So hard. Is there a way I can simply delete this term from my root by introducing some ideas? That is exactly called Smith's predictor. That you can literally remove this guy, literally remove this guy from your loop. Wow, this is magic number 2. I'm showing you how to do it. Called Smith's predictor based control. We can remove this thing out of it. Okay, let's do it. Okay, so the idea still, I'm using a non-traditional, non-classical approach based on what we learn about the Youla parameterization. So what we want to do here is, so I hope this whole system, the T, is still like Cp divided by 1 plus Cp times E minus Ls. So basically I deleted this thing, so delete this thing from the denominator. Because in the denominator, you have this term, you will complicate the way to compute the characteristic roots. It is no longer a simple polynomial. Yeah, you have something you cannot simply erase. It's hard to do. What we do here is, okay, so basically listen carefully. So I have, we do this. So, we do the same idea here. So let me put, so I have an original system in here. Okay. Then remember I said that I put, no. I'm sorry, this is bad habit. So, no. Do this. So I pull out this signal. I make a copy of it. Okay. So this is negative. This is positive. So this is 0. Okay. Okay. But I'm still using this thing into my feedback here. Okay. But what I should put it here. So you know that. So this one will be PELS. Then, but I have C1 plus CP here. Okay, I have 1 C over 1. So this one will is the same like this. So in fact, everything I should put here is C over 1 plus Cp in here, right? Is that right? Okay. I should put something in here, right? But remember, what is C? What is so this is let's say this is U, this is E. So how you can do that? E goes to C, so it's like you have C in here. So you have C in here. It goes to C. Then you get a P in here, right? So then you got this is a minus here. Okay, don't be. So this is a minus. Okay, this is a minus. So this is my U. So this box will give me what? C over 1 plus Cp, right? 1 plus Cp. So you can see that if I can design something like this, okay, then what's the closed loop transfer function? Is C1 plus Cp times Pe minus Ls. So then in this case, compare originally this guy. So as if I erase this term from my denominator, right? So isn't this a magic? Yes, done. But in this case, we have to do something careful. So basically, I want to say that, then tell me what is your controller. So my controller is from here to here. So this is my controller. This is my controller, okay? So this controller is actually called Smith's predictor control. Why call that? So this is different to the textbook interpretation, but if I insert this guy to here, what I'm going to get? And I do some moving something here. So what I'm going to get is, let me redraw this picture with you. So it becomes, you have a reference, you have output. So here you have a C in here. Remember, you have something P in here, okay? Remember, we have something here, minus, here's minus, there's the minus. So I insert this one into here, right? I write it this way. So now here I have PELS. So this is my original system I want to control. But I'm going to put this Y in here, pull out to here. So, but remember, I have another one that is from U. Then you have U times this one and negative, then negative. So you add basically. So you have U, the same U. This is U. Okay, you want to add this one in front. Okay, add this one in front. So you add something in here in E. You add. Okay, you add something in here. Okay, but when you say add, then it's same thing like you put a negative sign in here. So you put a negative sign in here, then you have a negative sign in here, then it's add, right? So it's supposed to add into here. So again, let me draw this onto you. So you have a signal here, you have a U in here, you have U in here going through this negative, remember. Then negative again, so positive, you add this one is positive. So I have a U in here, I go through a PELS, okay? Then I go negative here, I go to negative here again, so it's as if I add, so I don't need this. So this is not needed, okay? So with that, I'm going to draw nicely because these are negative, right? So negative. So basically I can draw something like this. C, no, let's do this. So you have C of S, you have PELS in here. So then you have a U in here. What I do is I do P, okay, 1 plus, okay, no, 1, sorry, it's 1 minus 1 minus ELS, okay? Because this add to this one, this is minus to this one, then times P. Then you put this one is minus in here. This is your reference. So this is something from here. So this is why. So usually people call this block diagram. So this is minus, this is positive. They say this thing together is called Smith predictor control. Okay. So at time t, you have a u of t, right? And u of t, so u of t goes through PELS, then you get y of t, okay? So y of t is measurable, okay? Measurable, okay? Okay. But if you have a u going through p, what's this? I don't know. This is actually equivalent to you have y of s goes through ys going through back LFS. So it's not delay, okay? So this is future. So then this signal is this signal, okay? So in other words, u times p is a prediction of y is t plus L. So this p, so this p thing here, okay, u times p is actually y t plus L. So this is future, okay? This is the future. And while u p e l s, this is y. You can get this one by measuring, but you cannot get this one, okay? So this is a prediction, okay? This is prediction. So you put this way because you know the plant, you know this one. So it's implied in here, there's a prediction here. That's why it's called Smith predictor controller architecture. By doing that, okay, you will be able to have a closed loop transfunction that is CP1 plus CP E minus LS. Okay, compared to if you don't have this term, if you don't have this one, Smith predictor block, your feedback, your closed loop system is CP 1 plus CP E L S in the denominator. Then you have E. Okay, so this is like a magic tool. You delete this thing completely. But this one has a price to pay, like you did some sort of prediction here, right? But it's totally realizable, so it's practical. Well, I used exactly the 45 minutes to cover 3 topics that is usually don't learn in classroom setting, in the textbook. So one is called internal model principle. One is called Youla parameterization. And I used the Youla parameterization idea to introduce you Smith predictor. And in the Smith predictor, I also pinpoint you that why Smith predictor can have a magic, can have the second magic about removing that. Oh, why write it bigger and bigger? Removing this term from my denominator is because of this Smith predictor mechanism I produced there. And in there, the essence of that is to introduce some prediction here. Of course, this is not physical, but in reality, you can implement this. So with that, I'm going to pass the time to Hiro. And so let me see. Questions? I'm going to give you this notes, but please read the files I put in the week 11 notes. So IMP is internal model principle, read this one. Youla parameterization, read this one. And Smith predictor, read this one and this one, okay? So that in the future, when you work with a plant with lots of delays, no worry. You have a secret weapon called Smith predictor control, okay? It will not mess up your stability. So 3 things we learned: IMP, Youla parameterization, and Smith predictor. So I'm going to stop.